Introduction. Storms are far more than strong winds or heavy rain. They are among the most complex, powerful, and awe-inspiring weather systems on our planet. Often described as a giant heat engine, a storm draws its energy from warm oceans and the dynamic interactions within the atmosphere. Understanding how storms form not only satisfies scientific curiosity, but also plays a crucial role in improving prediction capabilities, raising public awareness, and reducing the devastating impacts these natural disasters can cause. 1. What is a storm? Essential scientific concepts. In meteorology, a storm, commonly referred to as a tropical cyclone, is defined as a large rotating weather system, typically 500 to 1,000 kilometers in diameter, that forms over warm tropical or subtropical oceans. It represents a state of extreme atmospheric disturbance, characterized by organized convection and a closed wind circulation. A fully developed tropical cyclone consists of three major structures. The eye wall, a dense ring of towering clouds, sometimes reaching 15 to 18 kilometers high. This is the most violent region of the storm, containing the strongest winds, heaviest rainfall, and the most intense thunderstorms. The eye, a deceptively calm, clear zone at the center of the storm, marked by sinking air and extremely low atmospheric pressure. It is surrounded by the eye wall, where the storm's maximum destructive power resides. Spiral rain bands, bands of clouds and thunderstorms that extend outward in a spiral pattern from the eye wall, often producing intense rainfall, gusty winds, and localized tornadoes. 2. Why do storms form? The three golden conditions. Scientists have identified three essential conditions required for a storm to form: heat, moisture, and spin. 2.1. Ocean heat. The primary energy source. Storms cannot exist without warm ocean water. Sea surface temperature. The ocean must be at least 26-27 degrees Celsius, and this warmth must extend to a depth of around 50 meters or more. Such temperatures produce intense evaporation at the sea surface. Latent heat release. Water vapor rising from the warm ocean carries vast amounts of hidden, latent heat. When this vapor condenses into clouds and rain, the heat is released into the atmosphere, fueling the storm. The warmer the ocean, the more energy is available, and the stronger the storm can become. 2.2. The Coriolis force, the mechanism of rotation. The Coriolis force, generated by Earth's rotation, causes moving air to deflect from a straight path. This deflection prevents air from rushing directly into the low-pressure center, forcing it to rotate instead. Formation regions. Storms cannot form near the equator, within about 0 to 5 degrees latitude, because the Coriolis force there is too weak to produce rotation. They typically develop between 5 to 20 degrees latitude in both hemispheres. Direction of spin. Counterclockwise in the northern hemisphere to clockwise in the southern hemisphere. Without the Coriolis force, tropical cyclones simply cannot form. 2.3. Atmospheric instability, the vertical engine. A storm needs the right atmospheric environment to grow. Low vertical wind shear. If winds change too abruptly with height, the storm's structure is tilted or torn apart. Low wind shear allows convection to remain vertically aligned. Strong upward motion. The air must be warm and unstable so that rising motion continues, deepening the central low pressure and reinforcing the storm. 3. The formation and life cycle of a storm. The development of a storm follows a chain of interconnected steps. 3.1. Formation and development stage. Beginning with a disturbance. Every storm begins with a small-scale atmospheric disturbance, such as a tropical low-pressure area. Over warm ocean water, hot, moist air rises vigorously, lowering surface pressure even further. Development into a tropical depression. Surrounding air flows inward to replace the rising air. Under the influence of the Coriolis force, this airflow begins to rotate. Thunderstorms cluster and organize. When sustained winds reach 39 to 61 km/s, Beaufort 6-7, the system is classified as a tropical depression. Strengthening into a tropical storm. If conditions remain favorable, the system intensifies. Continuous evaporation and condensation release heat, accelerating upward motion and strengthening the circulation. When winds exceed 62 km/h, it becomes a tropical storm and is assigned a name. 3.2. Mature stage, the fully developed storm. At maturity, the storm achieves maximum organization and intensity. Complete structure. The eye wall, and spiral rain bands are fully formed. Central pressure reaches its lowest values, while wind speeds peak. The storm behaves like a self-sustaining heat engine. Warm air spirals inward, rises violently in the eye wall, and spreads outward at the top of the system. Formation of the eye. Two key processes create the eye. 1. Centrifugal force from the rapid rotation keeps outside air from entering the core. 2. Subsidence, sinking air in the center warms adiabatically, causing clouds to evaporate. This produces the iconic calm, clear, and deceptively peaceful center surrounded by extreme violence. 3.3. Weakening and dissipation stage. A storm weakens when its energy supply, warm ocean water, is interrupted. Movement over land. Moisture supply is cut off, and friction with terrain disrupts the storm's organization. But movement over cooler water, 26 degrees C. Reduced heat and moisture cause the storm's convection to collapse. Unfavorable atmospheric conditions. O. Strong vertical wind shear. O. A dry air intrusion. I.O. Cold air entering the system. All of these factors disrupt the storm's structure and lead to dissipation. 4. Climate change and its influence on storms. Modern climate research shows that global warming is significantly affecting tropical cyclones. While the total number of storms worldwide has not necessarily increased, their intensity and behavior have changed. Rising ocean temperatures. Warmer oceans provide more fuel, enabling storms to intensify rapidly and reach higher peak strengths. The phenomenon of rapid intensification, in which wind speeds increase dramatically in less than 24 hours, is becoming increasingly common. A warmer, wetter atmosphere. A warmer atmosphere holds more moisture, about 7% more for every 1 degree Celsius of warming. This results in heavier rainfall, increasing the risks of flooding, landslides, and catastrophic storm surges. Conclusion. From a small disturbance in the tropical ocean to a massive system capable of releasing energy equivalent to dozens of nuclear bombs every second, a storm's formation is a remarkable demonstration of nature's power. Understanding the life cycle of a storm helps us respect and prepare for these phenomena. With continued advancements in forecasting technology, satellites, and atmospheric models, we can look forward to more accurate predictions and improved disaster preparedness, reducing losses and safeguarding communities in the face of increasingly powerful storms.